All right, team, today we're going to talk about 3.1 inverse functions. So we're going to cover these four main things. So first off, we'll talk about what an inverse function is. We're going to talk about how you can tell if a function is going to have an inverse. And if a function doesn't have an inverse, we're going to talk about what we do in that situation. We're going to talk about how to find an inverse of a function. And lastly, we will talk about how to verify if two functions are in fact inverses of each other. So to start with, we are going to talk about what an inverse is. Well, an inverse function is a lot like an inverse operation. So you already know all the inverse operations. Addition is the inverse operation of subtraction. Multiplication is the inverse operation of division. So inverse operations undo whatever the initial operation is. So an inverse function is going to be a function that undoes the original function. Okay, so it's going to be the total opposite. It's going to completely undo it. So how do we know? If a function has an inverse? Well, the function has to be 1-to-1. And so you should have this in your vocab notes here. A 1-to-1 function, what that means, let's define that down here. A 1-to-1 function means that each value in the range is associated with exactly one value in the domain. Okay, so what that says is each y value has exactly one x value associated with it. So what would that look like graphically? So an example of a function that is 1-to-1, for example, would be a linear function. Notice that each y value is unique. It starts out being a function, meaning it passes the vertical line test, and there are no repeated y values. That's what it means to be 1-to-1. Each value in the range is associated with exactly one value in the domain. Something else that would be a 1-to-1 function, say, would be the square root function. Again, there's no repeated y values. A non-example would be like a quadratic function. Notice here we actually have repeated y values. We have this y value twice. So y values get duplicated. This means it is not a 1-to-1 function. So what do we do with these functions that we know they're functions, but since they're not 1-to-1, they don't have an inverse? Well, what we do is we restrict the domain. So for example, for this quadratic function, we would go and we would say, for example, that x would be greater than or equal to 0. So we would only be looking at the right half of the graph. Now this would be 1-to-1 because now each y value is unique. I could have also said that x would be less than or equal to 0, and I would be looking at the left half of the quadratic function, but most often we restrict the domain just to be positive x values, but I could have very easily had done the negative x values. So a really quick visual way for us to inspect whether or not something is a 1-to-1 function is we can do what's called the horizontal line test. So the horizontal line test works just like the vertical line test, except it's going to be going horizontally to check for duplicate y values. So notice my linear function and my square root function, wherever I draw my horizontal line, it's only touching the function in one place. If I look over here at this quadratic, wherever I draw my vertical line, notice I'm touching that function twice. So that is not a 1-to-1 function. But if I move to the function with the restricted domain, whether it be the left half or the right half, I'm passing that horizontal line test. So the horizontal line test is a test to check if a function is 1-to-1. All right, next up, we are going to talk about how to find an inverse of a function. And I have 4 steps for you. 3 of the 4 steps are very straightforward, and the 4th one is the one that's going to require the most work, and it just depends on the type of function that you're working with, about how much work you're actually going to be putting in. So step number 1, I want you to replace f of x with y equals. Step 2, you're going to swap the x and y value, or values. For 3, you are going to solve that new equation for y. And then number 4 is just notation. You are going to replace y equals with this new notation, f inverse of x. And that's how we read that. Since my function started with f, my inverse is also going to be with respect to f, and we read this f inverse of x, and that's what that little -1 in the superscript, what that denotes is just we are finding the inverse of that function. So step 3 is actually just going to be the hardest of the 4 steps, and it just depends on how ugly your function is. Let's go through a few examples and we can see exactly what I mean. So our directions would be to solve or find the inverse of f of x equal to 3x minus 1. So we're going to start with this linear function here. So step 1, we're going to take the f of x and we're going to replace it with y equals. Step 2, we're going to swap places with the x and the y. And then step 3, we are going to solve step 2 to look like y equals. So first thing I need to do is add 1 to both sides. So x plus 1 equals 3y. And then the next thing I'm going to do, I don't want 3y, I want just y. So I'm going to divide both sides by 3. This is going to yield y equals x plus 1 all divided by 3. If you want, you could clean this up and you could say 1/3 x plus 1/3. Either is fine. And then step 4, you're just going to say that, hey, I did all this work to find the inverse, so I'm going to make sure I use the correct notation to denote that inverse function. So this is where you could say either of the 2 functions. So f inverse of x would be equal to x plus 1 all divided by 3. Now I just want to sketch a little picture and talk about what inverse functions look like with respect to each other. So let's graph the initial function. We'll make that one the red function. So let's graph 3x minus 1. So start down here at -1, that's going to be your y-intercept, and we're going to go up 3, and we're going to go over 1. Or I could go down 3 and to the left 1. So that's going to be my that's going to be my original function. We'll use purple, and we're going to go ahead and graph the inverse function. So graphically, I might use this one. It might be a little bit easier to work with. So that tells me my y-intercept is not ideal, but it's at 1/3. So I'm going to go up 1 and over 1, 2, 3. Or I could go down 1 and over 3, just to get a really quick sketch of that line. So there's my 2 functions. Here's my inverse. And then the green was my original function. And I want you to look at the relationship between these 2 functions. I'm going to actually sketch in this line right here of y equals x. And I want you to notice that they're actually the reflection of each other over this line, y equals x. You can see it's reflected over that line. And that's true for every inverse. They're reflected over the line y equals x. And hopefully that makes sense because you actually swapped places with the x and the y values. So it would make sense that you're going to get that reflection over that line y equals x. All right, let's try another one that's a little bit uglier. So let's find the inverse of x squared plus 1. Now, this is a quadratic function, and we already decided that quadratic functions are not one-to-one, therefore they do not have an inverse. So what we have to do is we're going to have a little bit more information for this quadratic function. We're going to need to know the restriction. So we're going to say for x values greater than or equal to 0. So I'm going to be looking at the right half of this graph. I very well could have said x is less than or equal to 0, but I went with the positive x value. So I'm only looking at that right-hand side of the graph. So if I'm just looking here, that tells me that function is in fact one-to-one. And if you want to know why it has to be one-to-one in order to have an inverse, think about the original function here. Here's this quadratic function. If I reflect this over the line y equals x, I get something that looks like that. And notice this is not a function. So if I'm finding an inverse function, it needs to remain a function. That means my original function that I'm working with has to be one-to-one. So if I'm only working with this right-hand portion, then I'd only be working with that top portion of my inverse. And you can see I have that nice reflection over the line y equals x. All right, for this one, why don't we start with something interesting? Let's look at domain and range, and then we're going to relate it to the domain and range of our inverse function. So this is a quadratic, and notice it has a restricted domain because we need it to be one-to-one. So this right here actually tells me what my domain is. It's going to be from 0 to infinity, inclusive on 0, because it has to be greater than or equal to 0. And then the range, this is a quadratic function opening up that has been shifted up 1 unit. So my range is going to go from 1 to infinity. So let's keep that in mind and we'll revisit that at the end of the problem. So step 1, replace f of x with y equals. Step 2, swap places with my x and y. Step 3, solve for y equals. So round 1, let's go ahead and take away 1 from both sides. So x minus 1 equals y squared. And then we're going to go ahead and square root both sides because I need to isolate y and I need to get rid of the square. So I do that by taking the square root. Now keep in mind when I square root something to help me solve for a value, I need to account for both cases and I need to have the plus or minus on there. Now, what I need to think about here is I'm restricting it to my x values greater than or equal to 0. So that means I'm only actually looking at the positive or the principal square root for my function. So we're going to have y equals the square root of x minus 1. If x was less than or equal to 0, then I would have negative square root of x minus 1. So step 4 is just cleaning up my notation. We had a function f. I'm now finding the inverse. So f inverse of x is going to be equal to the square root of x minus 1. Now let's take a look at this graphically. Let's look at our original function. We'll make this the green one. And I'm only looking at x values greater than or equal to 0. So I'm starting here and my quadratic does something like that. Now, my new function, my inverse function, is going to be reflected over the line y equals x. And I can also think about, I know how to graph a square root function. This has a minus 1 right here, so that means it's shifted to the right 1 unit, and it's going to look like a square root function. So it's going to look something like that. And then I can go ahead and if I want, again, draw that line y equals x, just to kind of visualize what that inverse function is going to look like. If I only knew the green portion of my picture was the original function and I didn't actually have the function rule to define that function, I could sketch in that pink function just based on the fact that I know an inverse has to be reflected over the line y equals x. Now let's check out the domain and range of this new inverse function. So the domain of my inverse function, well, you can kind of look at the graph or you can look at the function itself. 0 is the smallest number that I can take the square root of. So what number minus 1 would give me 0? Well, that would be 1. And I can also see that my x values over here start at positive 1, and then they get bigger. So my domain is from 1 to infinity. And my range, well, my y values start at 0, and they go off to infinity. Now, the interesting thing about inverse functions is notice the domain of the original function is equal to the range of the inverse function. And if we go and look at the range of the original function, that is equal to the domain of the inverse. And hopefully that makes sense. If you are taking all of the x values that were the domain of the original function and you're swapping places with the y values, that means you've moved the domain to the range position for the new function. And same idea with the range. You're taking all of those y values for the original function and you are swapping places with them, and they are now becoming the x values or the domain of the new inverse function. All right, let's try probably our ugliest one here. So the trickiest one to solve for would be a rational function. So let's go ahead and look at one. So let's define f of x as 3 minus x all over x plus 3. And let's identify domain and range here. So domain, if this is a rational function, we need to look and see what is going to make 0 in the denominator because we can't divide by 0. So that tells me negative 3 is the problem number. So I'm going to skip over negative 3. I can have negatives in the denominator. I can have positives in the denominator. I just can't make 0. So negative 3 is what makes 0 there. And then when I look at my range, I'm going to identify the horizontal asymptote. So I'm going to look at the coefficient since I have the same degree on top and bottom. I'm going to look at the ratio of my coefficients. So negative 1 over 1 tells me my horizontal asymptote would be at the line y equals negative 1. So that tells me I need to skip over negative 1. I won't have any y values that are equal to negative 1. So here we go. Round 1, f of x becomes y equals. Step 2, x and y swap places. Step 3, we solve for y equals. Notice this equation has two different y values. Okay, there's one in the numerator and one in the denominator. First thing we need to do is get rid of the y plus 3 in the denominator. So if I multiply both sides by y plus 3, multiplying and dividing by the same thing are going to undo each other. So this is going to leave me with x times y plus 3 on the left equal to 3 minus y on the right. Let's distribute our y. And what this does is this now allows us to move terms to either side, so that way I can get all of my y values together. So I'm going to add y to both sides, and I might even in the same step go ahead and subtract over this 3x term. So that way in one step I get all my y's on the same side and everything that doesn't have a y on the other side. So that's going to leave me with x plus y on the left, and then 3 minus 3x on the right hand side. Now what this allows me to do is my y's are on the same side, so notice each one of those terms has a factor of y. So I'm actually going to factor out that greatest common factor of y. So y times what would give me xy? Well, that would be x. And y times what would give me y? That would give me 1. I notice if I redistributed that y, I would get back to what I had in the step before. And what that did right there is it allowed me to turn that into a multiplication problem. Y times the quantity of x plus 1. So we get rid of multiplication by dividing. So I am going to divide both sides by the quantity of y plus 1. So this tells me that y equals 3 minus 3x all over x plus 1. So this is my inverse function. It's not pretty, but that's what it is. Now let's look at domain and range for this inverse function. So my domain, we can take a look at the denominator. What would make 0 in the denominator? Well, that would be negative 1. So we cannot have negative 1, so I'm going to skip over negative 1. And then for my range, we can look at the ratio of the coefficients, since we have same degree on top and bottom. So -3/1 would give me a horizontal asymptote at -3. So -3 is what I need to bypass. And just like what happened in the last problem, notice that the domain of the original is now the range of the inverse. And then the range of the original is the domain of the inverse. And that will always be true if they are inverse functions of each other. All right, so that gives you an idea on how to go through and solve for these inverses. Something else that you might be asked to do is to verify if the given functions are inverses of each other. So the way we do this and what we algebraically check to see if two functions are inverses of each other is f of g of x would have to equal x and g of f of x would have to equal x. And that might seem kind of weird to use function composition, but think about it. Whatever goes into my function f, so if I take g of x, and notice my input in g is x, so I plug something into g, I then plug that value into function f, I get out the original input. Something went in, something happened, something should undo that. I'm left with the original or the initial value. Same thing over here. If f goes in, or if x goes into f, which then that whole thing would go into g, I should get x out if they are inverses. So if f of g of x and g of f of x are both equal to x, then we would say f of x and g of x are inverses of each other. So let's try one. What if I give you g of x equal to 5x plus 4 and f of x equal to x minus 4 all divided by 5? So if we were asked to determine if these two functions are inverses of each other, then we are going to be testing both directions. We're going to test g of f of x and we're going to be testing f of g of x. It doesn't matter which one I do first, I can do either. If I get one direction that doesn't work, then I'm done. I'm going to stop. These functions are not inverses of each other. If I get one that works, I absolutely need to verify that the other one is going to work as well, because remember, function composition is not commutative, so there is no guarantee that one direction is the exact same as the other direction. So let's try g of f of x. So this will be g of 4 minus 5 all divided by, x minus 4 all divided by 5. So go to function g, and wherever there's an x, we are going to substitute in where our new input value is going to be. Multiplying by 5 and dividing by 5 undo each other. So I'm left with x minus 4 plus 4, which yields just x. So we have verified that g of f of x is equal to x. So one direction works. So let's try the other direction. Let's find f of g of x. So this will give me f of 5x plus 4, and we're going to go ahead and plug that in for g. So go to function f, and wherever there's an x value, you are going to substitute in whatever it is that they tell you to do. So instead of x minus 4 up in the numerator, we are going to have 5x plus 4 as my new x value, and then take away 4. And all of that will be divided by 5. So let's clean up the top. 4 minus 4 is 0, and 5x divided by 5 is going to give me just x. So then we have verified that f of g of x is equal to x. So we verified that direction. So we have actually shown now that f of x and g of x are inverse functions. Now, you're probably wondering, why couldn't you have just taken one of the functions, found its inverse, and then compared it to the other given function? Well, that's not algebraically determining or proving that two functions are in fact inverses of each other. Because if they are, we do have to meet this criteria right here, that when one function gets plugged into the other function, it's going to undo that initial function and leave you with that original input. So that's actually what you're doing when you are verifying algebraically that two functions are inverses of each other. Now, for example, let's do something that looks kind of close to this, and I'll show you what happens when these are not functions or not inverse functions. So what if we had g of x equal to x plus 4 all divided by 5 and f of x equal to 5x plus 4? I'm going to try one of the directions. So this would be g of 5x plus 4. So let's substitute in 5x plus 4 where there's an x in function g. And then notice I'm not getting the same stuff to cancel out. So like 5x plus 8 all divided by 5 does not simplify down to x. So I would go back and, double check my algebra and everything and make sure I didn't mess up like terms or anything like that. But because I didn't get x out, we can say that f and g are not inverses of each other. All right.